I'll start by thanking the organizers for giving this opportunity to present. Today I'll talk about how non-trivial topology of band structure in three-dimensional semi-metals leaves distinct imprints in the magnetotransport. Okay, so 3D semi-metals, the band crossings touch at certain points in the Brillouin zone that we have been seeing, and depending on the symmetry we can have various kinds of nodes, for example Dirac node, Weyl nodes, nodal ring and nodal planes, and it is these band touching points where interesting physics happens. So our goal is to extract the linear response theory, for which we use the concept of wave packets to describe the quasi-particles which are centered at R and K, and the phase space evolution is governed by the Boltzmann transport equation within the relaxation time approximation, and the quantum effects are captured by the Berry phase introduced topological quantities which are Berry curvature, and I will introduce another quantity which is the orbital magnetic moment. And the interesting thing is this, without the Berry curvature this term would not be here in this Hamilton's equation, which we in turn feed into the Boltzmann transport equation. So this is the backbone of everything that I will show you today. So the two topological quantities, Berry curvature we have been seeing, which acts like a magnetic field in the K space, and the other thing is orbital magnetic moment, which arises due to the self rotation of this wave packet, and it gives rise to Zeeman-like correction in the Bloch energy dispersion. So the corrected energy will be the Bloch band energy plus the energy correction due to the orbital magnetic moment, which in turn will be fed into these equations and they go back to the Boltzmann transport equations. So a lot has been said and talked about Weyl semi-metals. They are great, but they are the simplest case where we have two band crossings, but nature offers us something more. We can have multifold band crossings as well, which carry large topological charge, and it is expected that they will give rise to richer transport properties. So here is an example of a certain material, cobalt silicide, where we can have at these high symmetry points spin 1 kind of excitation, and at R point 2 copies of Weyl excitations, which will take into account the Nielsen-Inomias theorem constraint. We can also have something like this, where we have 4-fold excitation at the gamma point and 6-fold excitation at the R point, high symmetry points, and these are the certain candidate materials which can host such nodes, which experimentally also have been verified for certain materials using RPACE, etc. So chiral anomaly, which gives rise to transport properties, as we know that in presence of non-vanishing electric and magnetic field, charge gets transported from one node to another. So the two nodes that I will be talking about is the RSW kind of excitation, Rarita-Schwinger-Weyl semi-metal, as well as triple point semi-metal, which hosts to the spin 1 excitation. So these have Chern number +4 if we add, and this has Chern number +2, and a flat band which has Chern number 0. So I will start with Rarita-Schwinger-Weyl semi-metal, 4 band crossing and linear band crossing near the nodal points. So we can see that the Berry curvature and the orbital magnetic moment, they both are band dependent, and the band have these numbers half, ±½ and ±3½. So the Berry curvature for the 4 bands is different, as well as the orbital magnetic moment for the 4 bands is different, which will give rise to richer transport properties compared to the Weyl case. As I said, the OMM changes the energy dispersion, and we can see while plotting the Fermi surface that in the absence of OMM we have perfect spheres, while in the presence of OMM and magnetic field in a certain direction, let us say, it squeezes the sphere in that direction. So the two concentric spheres now have been squeezed along this kx direction. This is our setup, planar Hall setup, where we have an electric field and a magnetic field within the plane at a certain angle theta. In addition, we wanted to see how strain will affect the magnetotransport. So we have, using elastic deformation, you can generate pseudomagnetic kind of field, which couples with also the chirality of the nodes. So the total magnetic field is this. Why this is interesting? Because if you have only E or B field, on Sagar-Casimirs constraints allow only to have even in B kind of terms, while in the presence of B5, linear in B terms are also allowed, which will be product of B5. Obviously the B square terms will be there, but linear in B terms are also there. So these are our results for the longitudinal response in the RSW, and we can see from the plots here B5 is 0, so only electric and magnetic field. So the blue solid lines represents the Berry curvature only contribution, while the orange dotted lines show the Berry curvature plus the orbital magnetic moment contribution, and we see that the overall effect is to decrease the response which we would get by Berry curvature only. Now talking about the two nodes which had different BC and different OMM, so one of them has been S is equal to half OMM enforces the BC, reinforces the BC, and S is equal to 3/2 opposes the BC, but when we sum over the two nodes, this is how the conductivities look like. Then we have the plots when we have B5 at certain angles, here 0 angle, here pi by 2 and 3 pi by 2, pi by 3. So we can see that the periodicity of the response has changed from pi to 2 pi, this because of the presence of linear terms. We also plotted the longitudinal response in with respect to B, and we also see once again that the OMM decreases the response in all the plots. So we have also calculated transverse response within the plane, which I am not showing keeping in mind time constraint, and the out of plane response we also get, which can be attributed to anomalous Hall effect and due to Lorentz force operator induced effect. The reason I am calling it an operator, because they have defined this Lorentz force operator which acts recursively on everything that appears to its right, and the out of plane response and anomalous Hall effect, we have kept the strain to be 0 because we wanted to see if our results matches with the experimental data. So this Nature Communication paper has done some experiments on cobalt silicide, and our theoretical results qualitatively matches with their experimental results. Next I will talk about ripple point semimetals. So because of the crystal symmetry and all, the Hamiltonian is D dot S kind of Hamiltonian, which is the generalized form of Weyl Hamiltonians, and like we can have multi-Weyl semimetals, here we also have multi triple point semimetals. So this parameter J can have 1, 2 and 3 values, and depending on the value of J, we can have linear, quadratic as well as cubic dispersion. So here I have shown the dispersion for J is equal to 2, which is quadratic case, and there is a flat band as well which has Chern number 0, and the magnitude of Chern number for the two dispersive bands is 2J. So again Fermi surface distortion because of the presence of magnetic field, and the Berry curvature has 0 magnitude for the flat band, but in contrast the orbital magnetic moment for the flat band appears to be twice, which is dependent on this factor Gs, and it's twice compared to the dispersive band. So the point is that if we ignore OMM, it appears that the flat band will not contribute at all, which is not the correct picture. So instead of plotting the whole conductivity, we just wanted to see qualitatively that how it appears. So here is the BC only dependence on By square and Bx square. We have plotted these functions only with respect to J, and here the OMM only parts have been plotted, the coefficient of Bx square and By square, and we see that for J is equal to 1, this within this range the OMM reduces the response, but it enhances the response for B is equal to 2 and B is equal to 3. Similarly, we see interesting interplay depending on J, whether the OMM will increase the conductivity or will it decrease the conductivity. Then transverse response also shows interesting interplay, that for J is equal to 1 it decreases the response, while for 2 and 3 it increases the response. We have calculated out of plane response as well, which again I am not showing. The point of calculating all this conductivity is that it gives you the complete picture of the whole magnetoelectric conductivity tensor. So now we have all the components, And in addition, we have also calculated the internode scattering. What happens if the quasi-particles can go from one node to another or vice versa, and these are our results which show it's a reason for appearing these kind of additional term purely from the chiral anomaly. And we can also have RSW node, like I said, two different kind of nodes. So say here RSW at gamma point and 2 copies of spin 1 at R points. Yeah. So these are our results. This also gives finite conductivity. So these are my summaries, that OMM will, ignoring OMM does not give us the complete picture, and it is essential that we keep it. Thank you.
One quick question. I understand the meaning of pseudo-spin.
Yeah.
The context of graphene as a sublattice wave function phase difference. How do you understand the pseudo-spin 1 or 3 or the conduct of semi-metals?
Yeah, so the pseudo spins are not actual spin which we will have in the relativistic case, because these are the azimuthal quantum number which are intrinsic properties.
I understand that, but in the graphene, you can identify the pseudo-spin as a phase difference between wave function and sublattice A and B. Also pseudo-spin law. So is there a way of understanding that in the sublattice structure?
So I can get back to you.
Can go for next speaker. We have time, so after that talk, if you have anything to discuss, we can.
Okay, thank you.